WebGL and JavaScript lets you do some really cool stuff. Just check out Odin. It's a demo I did for the new game conference in San Francisco. This is running directly in the browser. I'm currently working on the WebGL implementation in the Opera web browser, and as an old game developer, I think you can imagine I'm really excited about my work. I want the open web to be a serious game platform. WebGL is OpenGL ES2 for the web. ES stands for Embedded Systems, which means that not only can you run your 3D content across the desktop browsers, you can also have it running in browsers on TVs, set-top boxes, and mobile phones. It really makes HTML5 as the platform for games. In this video, I'm going to take you through a series of samples, starting with the most basic WebGL snippet possible and gradually building on that. If you want to follow along and write your own files as I go through these steps, you're going to need to set up a web server on your machine to host the samples. I've just set up a default installation of Apache, but if you have Python installed, you can also run this command from the folder you want to place your samples in. If you don't want to invest that much time or think this video is moving too slow for you, you can check out the finished samples online. A very good resource to have at hand is the WebGL API Reference card. You can find that on the Kronos website under WebGL. It covers pretty much everything you'll need as a WebGL application developer. The WebGL specification is also available from the Kronos website. Its intended audience are WebGL implementers, so it may not be the best resource for application developers. It is very lengthy and a bit hard to find your way around. One thing that is very handy in the spec though, is that it allows you to drill down into the OpenGL ES2 man pages, which gives you very detailed information about the API calls. OpenGL 1.0 was released in '92, and it featured direct mode rendering and a fixed function pipeline. Direct mode rendering meant that you pushed vertices into the pipeline one at a time. So to render a single triangle, you made a lot of API calls. You made one to begin drawing, 3 for the vertices, and perhaps a few for color and text chords, and finally one to finish. Fixed function pipeline meant that the graphics library was hardwired with a shading model, and you were allowed to set parameters on it, but essentially it was always doing the same type of shading. After 1.0 followed several 1.x versions of OpenGL, and they added things like multi-texturing, cube maps, and vertex buffers. By 2004, OpenGL 2.0 was released, and it added a programmable pipeline, allowing you to rewrite the shading model using the C-like language called GLSL. In 2007, OpenGL ES 2.0 was released. It's what WebGL is based on, and it's a modern version without the direct mode rendering, and it features a programmable pipeline. And then of course in 2011 at the Game Developers Conference, the WebGL 1.0 spec was released. We were there showing off an early version of the Odin demo, running in an Opera Labs build. It wasn't until 2009 and the OpenGL 3.1 release that the direct mode rendering and the fixed function pipeline was finally retired from OpenGL. Just a very quick overview of how the programmable pipeline looks. You can see the API to the left issuing draw calls and the actual data being fed into the pipeline in vertex buffers. The primitive processing collects the data in the different buffers and generates individual vertices. The vertices are then fed one after the other to the vertex shader, which will process the vertices and pass clip space coordinates along to the primitive assembly step. The primitive assembly steps looks at the type of the primitives you're drawing and converts the stream of vertices into individual primitives. That could include taking a 4-vertex triangle strip and converting it to 2 triangles. After that comes a clipping and culling step. Culling is removing primitives that are facing away from the camera. Once that's done, the primitives are passed one at a time to the rasterizer, and that will generate spans of fragments or slightly simplified pixels. Each fragment is then fed to the fragment shader one at a time to calculate the color. And then comes the depth and stencil test, which may discard the pixel if it's not visible. And finally, the pixel is alpha blended and possibly dithered before ending up in the frame buffer. Let's quickly look at the most important objects in WebGL. The context is the API for WebGL, and it also holds the OpenGL state machine. State machine sounds a bit fancy, but all it means is that you typically work on objects by first binding them to some bind point in the context with one API call. Then perhaps you're setting some additional state in the context, and finally you perform an operation that operates on whatever is bound to the bind point, using the current state set in the context. In OpenGL, there are a lot of constants used for bind points, formats, etc. For WebGL, all those are properties on the context. A buffer, or VBO as they're often referred to, is simply a buffer holding vertex or index data, and together with uniforms, it is the input data to the pipeline. A frame buffer, or FBO, is an alternative render target. There is a default frame buffer that you do most of your drawing to, but to do more advanced stuff, you may want to draw off-screen. In OpenGL ES2, the default is referred to as the Windows system provided frame buffer, but in WebGL it's just a regular FBO that displays its content in the canvas. A render buffer is something you can attach to an FBO to render into. It's not awfully useful, as you can also render into a texture, but currently the only way to use depth testing with an FBO is by using a render buffer. Note though that before you start rendering into an FBO, you should always check if it's complete, as what format you can use are implementation specific. The only thing guaranteed by the spec is that there is a combination that is valid. A texture is an image. You can use it both to read from in the fragment shader as well as setting it as a target for an FBO to render into. WebGL supports 2D and cube textures. A cube texture basically consists of 6 2D textures, one for each side of a cube. A program is both a vertex and a fragment shader linked together, and you always have to set a program as active to be able to draw anything. A shader is an object you create, set the source for, compile, and attach to a program. You can make it one of two types, vertex and fragment shader. The uniform location is an identifier you can query from the program. You use that to set constants in the program. You do something similar for attributes. Attributes are per vertex data as opposed to uniforms, which are global constants. But there's no special type for the attribute identifiers. They're just regular numbers. Okay, let's get started with our first sample. I'm going to save this file as o1-minimal.html. I'm going to add the doc type. Let's zoom that in a bit so you can see what I'm typing. And then we're adding an HTML tag. And we're going to need a canvas element. So we'll add that and we'll specify an ID for it so we can get a reference to it. And we're going to add a script tag. And get a reference to that canvas. And from that canvas, we want to get a WebGL context. The context is the thing that you're going to do all the operations on. So currently you get that by calling the method getContext and specify experimental WebGL. Okay, so on that context we want to set the clear color. And you specify 4 components, red, green, blue, and alpha. So we're specifying a blue color, and then we want to clear the color buffer. So there's 3 buffers you can clear, the color, stencil, and depth buffer. But we're just going to clear the color buffer, and that should be our entire sample. Should give us a blue square. Okay, so let's try to draw some actual geometry. We'll copy the last sample and we'll save this one as o2-minimal draw.html. We can remove those two lines, and let's specify a size for the canvas instead of relying on the default size. We'll make it 400 by 400 pixels. Okay. And to draw some geometry, we're going to need a buffer to hold some vertex data. So let's create a vertex position buffer. I'll create a buffer object, and let's bind that buffer to a bind point called array buffer. So there's another bind point as well, which is for indices, but we're just going to make a tiny buffer, so we're not going to use indices in this sample. Let's create an array to hold the vertices, and let me draw a little ASCII triangle so we can figure out the data to put in there. So while I do that, I can say that OpenGL uses a right-handed coordinate system, meaning that the x-axis goes to the right, and the y-axis goes up, and the z-axis goes out of the screen. So negative coordinates are further into the screen. Okay, so let's get the data in there. So we're just using 2D positions for this triangle. Okay, so let's fill the buffer with the data. And it's the buffer at that bind point. We'll pass a typed array containing the vertices. And we're going to say that we're going to upload the data once and draw it several times. That's the static draw. Okay, so let's create a vertex shader and a fragment shader. So we're going to need an attribute vec2 position. So that's our in data. And the one thing we need to do is to write to GL position. And GL position is actually a vec4, so we need to add 2 more components to the positions. And let's not worry about that for now. We'll just add on 0 and 1, and we'll discuss that later. So let's make a small fragment shader as well. For fragment shader, we actually need to specify the precision of the float type. There's low P, medium P, and high P. And high P is not mandatory, so some cell phones and set-top boxes won't have that, so only use high P if you must. So we're also writing to the GL frag color, and we're just going to give it a constant color, which is a green color. Okay, so let's create a shader program. Let's use some top-down design and pretend we have a method called create program text to strings. And the result of that is what we're going to set as the current program. We're also going to need to get attribute position, and we'll call the get attribute location method on the context, pass the program, and then the string, which is pos. So that's where we're going to send our in data to. So we need to enable that vertex attribute as an array. Okay. And then we're going to set the format of the in data. So it's vertex post attribute, and it's 2 component, and it's float, don't need to be normalized, and no stride and no offset. Okay, and then we just want to draw some triangles. We've got 3 of those vertices to draw and no offset. Okay, let's create this method called createProgram that we used before. So we're taking 2 strings as parameters, and we're going to return a program. So let's create a program object. And again, let's pretend we have another method called createShader that takes a string and the type of the shader. So we'll start with a vertex shader, and then let's call the same one again, but with a fragment shader. Okay, and then we need to actually attach those shaders to the program. Attach the second one as well, and then we need to link the program. So okay, link the program and then just return it. Okay, nearly there. So let's do the createShader function. So that's taking a string and a type. Okay, and we want to create a shader object. To specify the type of that, and then we want to set the source for that shader. That's in our string. Okay, then we want to compile that shader. And just return the result. And that is our second sample, and that should render a triangle. Let's save that and check it out. There it is, a green triangle. Okay, let's see if we can improve on this program a bit. Let's take those 2 utility functions and we'll pull those out into a separate file so we can reuse them easily. So we'll save that file as WebGL-utils.js. And we'll go back to the sample and we'll add a new script tag. We'll specify a source, WebGL util.js. Okay, let's make sure that still runs. Let's save that. Saved. Okay, that runs. Excellent. So let's try to improve these 2 functions a bit by adding a bit of error handling. So we want to check the compile status after we actually compile the shader. So we can do that by getting the shader parameter, which is called compile status. Okay, so if there is an error, let's use this event handler on the window object called onError. I'll add a handler, takes the message, the URL, and the line number. For production, you probably want to do something smarter, but for now we'll just use an alert. And we'll use this Visual Studio syntax on error messages that I'm used to, which is the URL and then the line number in brackets, colon, and then the error message. Okay. So if there is a problem with the compile, we'll just throw that error message. So we get the shader info log from that shader. I'll throw that string. We can do the same thing when linking the program. We'll check the program parameter this time. We'll pass the program, and we want to have a look at the link status. And if there is a problem, we'll throw that error message, and we'll get the program info log for that program. Okay, good. Let's see if we can catch a regular JavaScript parse error. There it is. Let's try an error in one of the shaders, just a regular syntax error. Okay, sorry, parse error, not syntax error. Excellent, so we've got some error handling. So let's copy the last sample and save that as o3-minimal shader.html. And we want to change that triangle into a square that covers the entire canvas. So we're going to draw a square. GL position takes clip space coordinates, meaning they range from -1 to 1. And we're going to draw that square by a triangle strip. That's two or more triangles connected. And let's put vertex 0 down in the left corner, 1, number 2 up there, and the last one. And let's input that data. Okay, let's change triangles into triangle strip. And it takes 4 vertices. And that should draw a square covering the entire canvas. Good. Okay. And we've got some hard-coded values down here. So let's actually add that to the buffer instead to just keep it in the same place. So the item size is 2. It's used in a vertex attribute pointer, and the number of items is 4. That's used in the draw erase call. So we'll replace those down here. Okay, just makes it a bit more generic, so the draw calls are actually using the data and the metadata. Alright, so the shaders are currently in a string. That's a bit awkward to work with. So let's add a script tag for the shader. So we're gonna specify an ID so we can actually get the content later. And we're gonna set the type. We're gonna use XShader for that. And we need another one for the fragment shader as well, of course. Okay, so let's add a bit of shader code. So we have the in data, of course, the attribute vec2 positions. Call it a vertex position. And then we have a varying. So that's data being passed on to the fragment shader. And we're going to pass a vec2 texture coordinate. I'll call that vTextCoord. And then our main function. And the text chord, we're just going to pass it the vertex position. So that's going to range from -1 to 1 as well. And then the GL position, just like last time, needs a vec4. So we'll add a 0 and a 1 to the positions. Okay, so let's do the fragment shader. So the precision, like last time, we'll use medium P for floats. And then this time we've got a varying, so we've got some in data to the fragment shader. We'll call the vTextCoord. And in our main function, we're just going to use the texture chord to set the GL frag color. And that's going to get clamped to 0 to 1 range. So it's going to be half the square is going to be black, or more than half the square. Okay, and let's not forget to change the strings. So we need to get those from get those from the script tags. We'll get element by ID. So it's the vertex shader, text content, and the same for the fragment shader. Okay, and then we need to change the string of the attribute location, because it used to be position, now it's a vertex position. Okay. So that should draw a nice gradient. So let's see if we can offset those texture coordinates a bit. We could just use a constant, but let's use a uniform. That's a constant that's passed into the shader program. So unlike the attributes, which are per vertex data, this one is just a constant passed in to the program. So uOffset, we'll just add that to the text chord, and let's create an array offset, and we'll just add 1 to the texture coordinates. So it's going to be in the range 0 to 2 instead. And we also need to get the location of that uniform. just like the attribute location, we need a uniform location. Okay, uniform location. And then we're gonna set that uniform. We'll use uniform to F, so we're passing two float values to that uniform. Okay, so this should be a mostly yellow square instead of a mostly black square that it used to be. Okay. So it's a little bit more code than the previous sample, but still not that much. Let's try it out. Cool. Okay, so let's take this little snippet of code that generates the screen quad and pull that out into our WebGL utility file, because that's a handy routine to have. So let's get the vertex pos buffer, and we'll get that from a function called screen quad, and we'll put that in the utility file. We'll create a new function, screen quad. Doesn't need any parameters. We'll paste our code there. Sort out the indentation, and we'll return that buffer. Buffer. Okay, and this is the reason I put the item size and num items on the buffer. So that's quite a bit shorter now. And let's see if it still runs. It does. Okay, so let's see if we can do something interesting in just a fragment shader. We'll copy the sample and we'll save that as 04 fragment shader.html. And we're gonna zoom that out a bit, and we'll change the size of the canvas to 900 by 900 pixels. And we're gonna try another way of getting the texture coordinate into the fragment shader. So we'll delete those two lines and that line, leaving just a minimal vertex shader. And we're not going to need the in data to the fragment shader, but we are going to need a constant, and that is the size of the canvas. So you're going to need a new uniform. To canvas size. Okay, and we're going to use something called GL frag chord, and that gives you the pixel position of the current fragment. So let's calculate the texture coordinate, and we'll use that GL frag chord, and we need to scale it by the canvas size. So frag chord XY, just need 2D positions here, so divide that by the canvas size and multiply it by 2, and then subtract 1. And that's going to give us the same as last time, but the non-offset version, so it's going to be mostly black. And we'll change the name of the text chord. Okay, and we need to delete the offset array, and we need to get the uniform location, but it's now called canvas size. Change the string as well. Canvas size. Okay, And we're gonna set the uniform. It's still 2 floats. It's a different location. Okay, and we've got a reference to the canvas, so we can just use c.width and c.height. Okay. Let's have a look. Cool. So for this fragment shader that we're going to make, we're going to need high precision floats. But like I mentioned before, it's not mandatory. So to be able to use that and still have it compile and link on devices, we're going to have to protect it with an ifdef that tells you whether the device actually has high precision floats. So we'll put an ifdef in GL fragment precision high. Okay. So if it supports high precision floats in the fragment shader, we'll use that. Otherwise, we'll use medium P. It might work still. And then we're going to use an integer for the first time. So we need to specify the precision for that. We'll use medium int. Okay. And we're going to calculate the color for every single pixel in the fragment shader. So let's make a new function. And returns a color, and let's just call it calc. It takes the texture coordinate as the only parameter, and it returns a color. Let's just use the same color as we currently set. So the texture coordinate and 0, 1. And let's use that calc function instead. Just needs the texture coordinate. Okay. Good. So let's see if that still works. Okay. So let's see if you can figure out what I'm going to do in this calc function. So I'm going to need an X and a Y. And then I'm going to have a for loop and iteration from 0 to, let's say, 100. And I'm going to do some calculations here. So I'm going to need an x temp, and that's going to be x squared plus, no, sorry, minus y squared plus the x texture chord. And y is going to be 2 times x times y, and add texture coordinate y component. Okay, and x is x temp. So if x squared plus y squared is greater than 8, then we're going to figure out a color. Okay, so that color is based on the iteration. So you might have figured out what I'm doing now. Let's call it D, and let's cast that float iteration. Let's just divide it by something, 20. Let's return a color. Let's make it a grayscale image and opaque. Okay, and if it didn't go in there, we'll just return black opaque. Okay, so what is this going to be? Let's try it out. It's a fractal. As you can see, the fractal looks quite banded, so let's look up Mandelbrot on Wikipedia. And under escape time algorithm, you can see the algorithm I used. And below that, there's smooth coloring, continuous smooth coloring. Okay, so in the shader, this is going to be awfully slow, but it doesn't really matter. We're going to use that continuous smooth coloring algorithm, and log of square root of x squared plus y squared divided by log of 2. I could have used the cached value and improve this in all sorts of ways, but it doesn't matter if it's a bit slow. Okay, let's try that. And it's smooth. It's a bit darker, but it's smoother. Okay, the cool thing though about fractals is that you can measure some other values and use that to color it a bit more. So let's add V and J. We'll initialize them to some large values, and we'll have a look at the minimum value for the x squared plus y squared, and we'll have a look at the minimal value for and these are absolute values for x times y. And we'll keep updating those in the loop, and we'll use those to color the fractal a bit more. So we'll add those into the red component and the blue component. Let's check it out. And that's a lot more color. Cool. It's not quite what I wanted though, so let's go back and we'll tweak those values a bit. I fiddled with this earlier, so I know I'm gonna invert that value and divide it by 2, and it's gonna look cool. We'll do the same with J. We'll invert it and divide it by 2. And that should give us a nice sort of halo glow to the fractal. Looks really cool. We can only see part of the fractal, so we want to offset and zoom it a bit. So we're adding a uniform vec2 u offset and a uniform float scale, u scale. Okay, so we need to get the uniform locations for those. Offset uniform. Okay, and the second one, scale uniform. Okay, so we need some actual values to put in there as well. So we'll create an offset array, -0.5 and 0, and then a scale. Larger value will zoom out. So, and we're setting the offset. It's 2f. Offset 0 and offset 1. Okay, and we're setting the scale, and that's using 1f because it's just a single float value. Okay, we need to modify the text chord in the fragment shader. So we are going to multiply it by the scale, and we're going to offset it. Sorry, we're going to add the offset. Okay, that should display the entire fractal. Cool. So let's see if we can make this interactive by updating the offset and scale. So we're going to need to draw it several times. So let's make a draw function. Okay, let's just call that once for now. And we're going to need some input. So let's store some actions and whether they are active currently. I'm going to need some key mappings as well. And I have these on a note. I don't actually remember these, but we're going to need some keys that map to actions. So we want to pan left, and pan up. So these are the key codes for the arrow keys. Pan right, and pan down. Okay, we also want to zoom in and zoom out, so let's add those. And 88. Zoom out. Okay, so let's initialize all the actions to be false to start with. So for every key mapping, we'll set the corresponding action to be false. Okay. And we're going to need some input handlers. So window on key down. Handle that. And we need to get the key code. I need it as a string. And if that is actually a key that we care about, i.e. it's in the key mappings object, then we need to set that action to true. Okay. Now we need to do the same thing for when you release a key. So let's copy the whole thing. And on key up, I just set the action to false. Okay, so we also want to keep redrawing as there's an action active. So let's add an interval. So let's go down to the key down handler again. And if there's not an interval active, we create one, and we want to draw, let's say, every 16 millisecond. Okay, now on key up, we need to loop through all the keys and check if there's any actions active. Okay, so if none of the actions are active, we need to clear that interval so we stop drawing. Okay. So we also need to update the offset. These are from my notes again. Actions pan left. Okay, that looks slightly complicated, but basically it just looks at the actions and pans it and takes the scale into consideration, pans it left and right, and we'll change that to pan up and down. And pan up. Okay, and then scale. So that's for zooming. So look at the zoom in and zoom out actions, and we'll just multiply it, or we'll multiply it by 1, which doesn't change it. The zoom out bit. So slightly complicated. I figured it out before I did this recording. Okay, we're in good shape. Let's check it out. So I'm actually recording this at 12 frames per second, so if the video might look a bit choppy, that's probably the reason. Just save some space on my disk drive. So as you can see, you zoom in, it eventually becomes pixelated, and that's the reason I needed the high precision, because you know you're zooming in quite far and eventually you're going to run out of precision, and that means it's going to be pixelated. But you know, it's really cool to pan around and zoom in and out. You can play with this for quite a while. So let's have a quick look at using textures. I have this Opera PNG texture added to the folder. And let's copy the O3 minimal shader sample. And we'll save that as O5 texturing.html. Okay, zoom it in a bit. So we're not going to need that offset because we want to have the texture coordinates in the -1 to +1 range for this sample. And we're going to need to add a new uniform. It's a sampler 2D. Call it uSampler. And instead of the constant color, we're going to look the color up in the texture. We're using texture 2D, and we need to pass it the sampler and a 2-component texture coordinate. Okay, we can delete that. And we need to get the right uniform location. Okay, and we need to set that uniform. Let's just change the size of the canvas first so we can see what it's doing. We'll set that uniform. It's an integer. And we're just going to use texture unit 0. Okay, and we need a texture. Let's create a new texture. Create texture. And we're going to need a new image to actually load the image data. And in the onload handler, we're going to do the actual drawing. So we're not going to draw anything until we've loaded the entire image. Okay. So we're starting off by setting the active texture. This is actually the default value, but I'm putting it in just in case you want to use a different texture unit. Then we're going to bind the texture as a 2D texture 2D. And then we're going to specify a pixel store parameter, and we're going to flip the image data in the y-axis, so we get it displayed in the right direction. And then we're gonna specify the image data. So it's the MIP level 0, and it's RGBA, and it's unsigned byte, so it's 32-bit RGBA texture. Okay. And then we want to specify some texture parameters. And it's for the texture 2D. And we want to specify the filtering parameters. So texture mag filtering, that's when it's displaying it larger than the original. We're going to use nearest pixel. And then we might as well specify the min filter as well. Zoom that out a bit. And the last thing we need to do is actually to set the source of the image. That's going to kick off the loading of that image. And once it's loaded, it's going to set it up and draw it. Okay. Let's have a look at that. There it is. So it's actually drawing a bit pixelated, as you can see when I zoom in, and that's the filter. So let's try another one, which is linear, and now it's gonna look all smooth and nice if I reload. Okay, it's also displaying 4 O's, and that's because it's indexing with -1 to +1. Let me just add a border up here so you can see where the actual canvas is. Okay. And the default wrap mode for texturing is to wrap around. So that's why it's drawing 4 O's. So if we change that parameter for the texture 2D, can change that to clamp, so only 0 to 1 are valid values, and you can see what happens then. We'll clamp it to edge. So that's for one of the parameters, the S parameter. We'll reload, and you can see it's not clamped. And we can do the same for the other parameter, clamping the T parameter to the edge, and that's just one. We've already seen how we could move the shaders from strings into a separate script tag, but let's take that one step further. We'll save this as 06 xhr shaders.html, and we're going to move the shaders out of the script tag and into separate files. So we'll create a new file, and I've created an empty folder called shaders. So we're gonna save these into there, and we'll call this one vshader-00.txt. You know, this is going to be useful when you have larger projects and you want to have a lot of shaders. We'll copy the fragment shader into a separate file as well, and we'll save that in the shader folder, fshader-00.txt. Okay, so we can remove the script tags, zoom it in a bit. Alright, so we used to get the strings from the script tags, but we're not going to do that anymore, so we can delete those. And in fact, we are going to delay all this setup code until we've actually loaded the shaders, just like we did with textures. So we're gonna put this into a function, and we'll call it init program. Take the program as parameter, and close that. Zoom it out a bit. Okay, so this one is going to get called once the shaders have been loaded and a program has been initialized. So let's pretend we have a function called load program, and we'll pass it the file names for the vertex shader and fragment shader, and we'll also pass it the callback to call when these are loaded. So let's say init program. Okay, and let's do that load program in our WebGL utils file. So function load program. Callback. So we've got to create a program object, of course. And to actually not do this too early when we've just loaded the first file, we're going to have two very similar functions that we call vShader loaded, and going to set the source on the program, and we're going to check if the other source has already been set. So if the shaderSource has been set, then we're going to call another function to link this program. Finally, call the callback and pass the program. Okay, so gonna need a very similar function. We'll call that fShader loaded instead. And we're setting the fShaderSource and looking if the vShaderSource has been set. Okay. And of course we're going to need to load some files. So let's pretend there's a load file function as well available. And we'll load a vertex shader and then a fragment shader. Okay. So let's do the function link program. All right. So we're going to need to create a shader. We'll specify the source and the type. So this is the one we wrote earlier, reusing that. And the same for fShader. Okay, I'm going to need to attach the shaders to the program. And same for the second one. I'm going to link the program. And we're just going to add some error handling. Can probably copy that from up there. Okay, that's our link program function. So we've got the load file to write. So function load file, take a file name and a callback, and we're gonna create XML HTTP request. It's a brilliant name. Extensible markup language hypertext transfer protocol request. And on ready state change handler. So this is just standard stuff. You can look this up by searching for XHR. You have a event handler that goes through a couple of different states, and you need to send the request when it changes to 1, and then once it reaches 4, you have the results or some sort of result. We'll add some common status code check. So this is if it succeeded, then we'll just call back with the content of that file, which is in the response text. And we'll add another common case if the status equals 404, then couldn't find the file. So we'll throw in a string error message. There. And else we'll just throw the status code. Status. I'll add a dot as well. Okay. So I think we just need to kick it off as well. So on the request, we'll call open and specify get. And that's going to start the loading, and then it's going to be asynchronous, and once we receive the entire file, it's going to call back and do all the rendering. So one annoying thing about this is that it caches results. So if let's add a no cache parameter. This is handy during development, so we're just gonna make it a random URL by using the question mark and add that to the URL, and just use the current time, and we'll get a random URL so it doesn't get cached. and change file to URL, and we'll add that parameter, and then we just need to make sure we specify that it shouldn't cache the files. Alright, that's it. Let's try it out. Good. So let's see if we can do for meshes what we did for shaders. I've added a mesh called torus.js. It has indices, positions, and materials in it. It's in JSON. You can read about JSON on json.org. So we'll copy the minimal shader and we'll save that as a new sample called 07 xhr mesh.html. And let's remove a lot of stuff here, and let's just write it the way we would like to be able to use a mesh. Delete that, and we get the context and create a new mesh, and on that mesh we call load. We specify the URL to the mesh, and we want to have a callback when it's fully loaded, and we'll just create an anonymous function that will call draw on that mesh once it's loaded. Really simple. That's the way we want to have it. So let's add a script tag and include that new file we're going to write. So mesh.js. So we'll create a new file. We'll call that mesh.js. And we'll start by adding a constructor for mesh. We'll just add in the functions we wanted to have. It was load, taking a file name and a callback, and it was draw. That didn't take any parameters. Okay, so let's start with the load function. So we're going to have to save the callback because we're going to need to call that later. And let's use the load file that we did before. So we'll pass it the file. And in the callback, we actually want to call an init function on this mesh. So we're going to need to get a closure on this object, and you do that by adding a variable. I use that most of the time. Assign this to that and use that in the function. I'll call init. Okay. And it also takes no cache. Let's add, because we're loading JSON and not XML, it's going to complain if we don't set the MIME type. So we'll check if it's JSON we're loading. Request, we override the MIME type. I'll set it to application JSON. Okay. So meshes we probably don't need to cache, but you can set them to cache if you want, and we'll set the JSON flag to true. Okay, so the init function, let's add that to the mesh. So it takes a JSON string, because that's what gets returned. And here's how you create an object from a JSON string. You just create mesh and you call JSON parse and pass it the string, and you get a JavaScript object. It's really handy. So we're going to create a new buffer to hold the position data, and I'm going to bind that buffer to the array buffer bind point. And we're gonna fill that buffer with the data. It's the array buffer bind point, and the data is in that mesh that we just loaded. So it's called mesh. What was it called? Vertex positions. And it's going to be static draw. Okay, so let's copy those because we're going to use indices this time as well. So let's make an index buffer, and we're binding that to the element array buffer bind point. And we'll specify the data for that bind point, and it's not going to be floats, it's going to be unsigned integers. And it's the indices. Okay. And let's keep a tally of the number of materials we need to load. So it's an array of materials. Let's get the materials length. So that's number of materials we need to load still. And we're going to generate an array of programs. So for each of those materials in the mesh description, we'll get a reference to that material. And we're going to create a program, and we're going to get that from the load program we wrote before. Returns a program. No, it doesn't. Alright, we'll actually add that in then. It should have returned a program. Okay. So, yeah, so load program returns that program. We need to specify the material. What was it called? Vertex shader. Yes, that's right. And then the fragment shader. There is. And also a callback. Okay, so we need a closure again. I'm going to call program loaded. Okay. And we going to set the number of indices to draw for this program. Let's call it num indices. We'll use that just to make sure it's not a typo. Okay, and then you shouldn't forget to push that program onto our list of programs. Okay, so program loaded. It's a function, takes a program. We're going to get the attribute location for the vertex position. And if this was the last program to load, so we've got a count of the programs. Then we're going to use that callback that we saved. Okay. So let's do the draw down here. For each of the programs, we are going to, let's get a reference to that program. Okay, and we're gonna enable that program. I'm gonna enable the vertex attribute array. There it is. Vertex position attribute. Okay, and we've got indices this time as well. So let's just bind the element array buffer. We'll bind the index buffer. And we'll bind the vertex buffer as well. Let's copy that. Okay, getting there. So vertex attribute pointer. This time it's actually 3 floats per position. So copy that, and 3 floats, and then no normalized. Okay, and then we need to use the draw elements because we have indices this time. So we're drawing triangles, and the number of triangles or vertices to use is in num indices, and the indices are unsigned shorts, and then we need an offset. So the programs are actually arranged in order, so we're starting on index 0, and we'll increment that every time we draw the triangles for that material, and we can use that as the offset. And we need to specify that in bytes, so we'll multiply it by 2. Okay, That was a bit of typing, but it's not that daunting. It's a nice mesh class. Let's see if we can save that and try it out. A mesh. So let's see if we can make this mesh look a bit more three-dimensional by applying some flat shading to it. We copy the last sample and we'll save that as 08-flat-shading.html. So we're going to increase the size of the canvas a bit, and we're going to load torus-normals, which is a mesh file I've prepared. So looking at that mesh, you can see it looks much like the last one, except a bit further down it also has vertex normals, 3 component float values that describes the surface direction at every vertex. So let's go to the mesh file, and we're gonna need another attrib location for the normals. So we'll call it vertex normal attribute, and the name is defined in the shaders. So let's have a look at what that mesh uses. It uses vShader02 and a yellow and green fragment shader. So these are shaders I've prepared earlier. So we'll look at the vShader. You can see it takes the position and normal 3 component float, and it passes the normal on to the fragment shader. And the fragment shader has a color and a made up light direction, and it calculates the diffuse value by taking the dot product of the normal and light direction, and that diffuse value is used to shade the mesh. So that was called a vertex normal. And we're also going to need to create a buffer to hold that data. So much like the position buffer, we're going to create a buffer to hold the normals. But first we're going to check if the mesh actually has some normal data. So that was called vertex normals, and we'll only do this if it actually contains normal data. So we'll create a new buffer, and we're going to bind that buffer. So this is per vertex data and not indices, so it's going to be the array buffer bind point. And we're going to upload the data into the buffer. So float 32 array as well, and static draw, and the actual data to put in that array is called mesh vertex normals. Okay, now we need to modify the draw function as well. So first we need to check if we should actually be using normals. So if we should use normals, then we'll enable vertex attrib array for the normals. And then we're going to bind the buffer. And we're going to call vertex attrib pointer to say what format the data is in. And it's 3 component floats, just like the positions. And that should be it. Okay, let's check it out. And nothing renders. So looking over the file, I'm actually speeding this up because it took me a while to find the typo. So there's a capital N missing. So save that again and try it out. And there we go, a flat shaded torus. We're going to start working on a matrix library. We'll save a new file as vectormath.js. We're going to use 4x3 matrices. We could have used 4x4 matrices, but we're mainly doing rigid body transforms, and for that 4x3 matrices are perfect. So we'll create the prototype for the matrix 4x3, and we'll add the functions we're going to need. We'll start off with a quite small set of functions. We'll start with the make, and that takes the X, Y, and Z axis and a translation, all 3 components. The next one is to be able to make identity matrices. So we'll add that in. And we want to be able to initialize with a rotation, and that's an angle and an axis to rotate about. And the final thing we want is the multiply, of course. Okay, that's a good start. Another very handy thing to have is to have a global model matrix. So we're going to create a little structure to hold that. We're actually going to expand on this later, but for now we'll just create a global GL matrix state, and we'll add the model matrix in. And we'll also add a function to get the current model matrix. So it's going to return that one. Okay, so we'll expand on that later, but that'll do for now. So to hold the data in the matrix, we're going to use a typed array, and we're going to use a float 32 array, and we'll make it 16 elements large. And the reason we're doing that is that's what we need to pass to WebGL. And the array is actually initialized to 0, so to make a identity we just need to fill out the diagonal with 1s. Now in our operations we're not going to actually assign to all the 16 elements. When we do our multiply we're going to ignore some of the elements, but it's really handy to have it laid out like that, so we can just give it to WebGL. So the make is a bit tedious to type in, so I'm speeding this up for you. The same with the identity. And for the rotate, we're gonna look at Wikipedia on rotation matrix. There's a rotation matrix from axis and angle. So here's the matrix we need to build. That's quite a lot of typing to do that. So again, I'm going to speed this up for you. Okay, and now for the multiply. We're going to look that up on Wikipedia again. And we'll search for matrix multiplication. So you can see an illustration of how to do that. And again, this is a lot of typing, so I'll speed it up. So the gain of using 4x3 matrices instead of 4x4 is actually that we'll save 28 multiplies and 21 adds for a single multiplication. And that's just because we're gonna have zeros and ones in a lot of the positions. So using 4x3 is a good choice. Okay, and that's our entire little matrix library. Okay, it's time to get some motion on that mesh to see that it's really 3D. I have this yellow cube mesh. It's a really simple cube, and it's using VS Cube and FS Cube as shaders. So these don't actually exist yet, so we're gonna write them. We'll start by doing the vertex shader. Save that as VS Cube.txt. And it is of course going to need the position attribute and the normal attribute, just like the last shader. And we're going to take a matrix, a 4x4 matrix that we'll call UM matrix, and that's for model matrix. And we're going to pass a world space normal to the fragment shader. So the normals and positions are in object space in the mesh, but we're going to use this model matrix to get it into world space. So you do that for the position by multiplying it with the model matrix, and we'll add a 1 as the last component. That means it'll actually use the translation of the matrix as well. For the normal, we don't actually want to translate it in space, so we'll add a 0 as the fourth component instead, and it'll just apply the rotation to the normal, which is what we're after. Okay, so that's our vertex shader. Let's do the fragment shader as well. I'll save that. FS Cube. So we're specifying the precision. Medium is fine. And we're taking that world space normal in as a varying. going to calculate a diffuse value. So just like last time, we have our made up light direction, and we're going to use the world space normal and get the dot product between those. And we're going to just dim it a bit by multiplying it by something smaller than 1 so it doesn't get too bright. And the color, we just use the diffuse value and we'll make a yellow color by using the red and green components. Okay, so there's our fragment shader. So we're gonna get we're gonna get a uniform location to that matrix. Okay, so attributes are per vertex data and uniforms are constants that you pass in. Okay, so we actually need to set that matrix before we draw as well. So we're going to create a function to set that for us. For now it's just going to set a single matrix, but later on it's going to set more than just a model matrix. So we'll call that set matrix uniforms. And it takes the program, and we had going to set that matrix uniform, and we made a function earlier to get the model, the global model matrix. So we're going to use that called model matrix, and it had a member that was called D. Okay, so that's the data in the matrix, which is conveniently 4 by 4, even though it's a 4 by 3 matrix. Alright, so let's create a new sample. Copy the previous, and we'll save that as 09 leaving flatland. Okay. So let's create a function to do the drawing, because previously we've just done this once. We'll just call mesh draw in this function, because to actually animate we're going to have to draw several times, of course. So when the mesh is loaded, we'll call that draw, and we're going to draw the right mesh, of course. So change that to yellow cube. Okay. So to actually, if we're going to draw it multiple times, we need to enable depth testing, and we should set a clear color as well. We'll use black. Okay. So we're going to need some parameter to let our animation depend on. So we'll create a Z parameter and we'll add to that every time we draw. And the first thing we want to do when we draw is to clear the color buffer and the depth buffer. So you can just OR those IDs together and it'll clear both of them. Okay, so let's make the model matrix rotate around the x-axis, and then we'll multiply that by another rotation. And let's create a matrix outside of the draw loop so we don't have to allocate and release that every frame. So a new 4x3, and actually I haven't included that vector math file, so we'll do that first before I forget it. Okay, so we have our rotation, and we'll make that rotate around the y-axis, and we'll multiply by that, and then we'll do the same for the z-axis. We should get a nice little spinning. Okay. So it's looking good. So now we want to actually draw multiple times. So on my blog I have this little shim for the request animation frame that I'm going to use. Let's copy that. Paste that in here. Okay. And then at the beginning of the draw, we'll call that on the passing the canvas element, so we'll get continuous updates. So let's check this out. And there you go, a spinning cube. You probably noticed that there was something that didn't look quite right in the last sample, and that was perspective projection. That's what makes things in the distance look smaller, and it's described on Wikipedia. We're going to add that to our sample, and to do that we need to use a new mesh file. So we're using yellow cube 2, and it has VS cube 2 and FS cube 2 as shaders, because that's what we need to change. So we'll copy the last sample. We'll save that as 10-perspectiveprojection.html. We'll change the mesh file as well. So let's copy the vertex shader from the last sample, and we're going to add another matrix. So we'll save that as cube 2, and the matrix is the projection matrix. So we'll call it UP matrix, and we're going to multiply the position by that. And let's look at the fragment shader. The only thing we need to do is to save that as cube 2 and change the sign of our light direction. Okay, so we'll add a new uniform location for the projection matrix, and we're going to set that in our set matrix uniforms function as well, and we'll create a new global projection matrix that we can query with that function. Let's go to our math stuff and we'll add that new function to get the projection matrix, and we'll add that to the state, to the global GL matrix state. We'll add a new matrix, projection matrix, and this actually has to be a 4x4 matrix because it's not a rigid body transform. So we're speeding it up and we're making a 4x4 matrix. You can see I'm filling out the missing elements that we haven't used before, creating a make perspective function, filling it out from Wikipedia. Alright, so we should also set some reasonable default values on the projection matrix. So we'll call our make perspective and we'll pass 45 field of view, square aspect, and near of 0.01 and far of 100. Okay, and we should also change the position of the mesh a bit so we can see it properly. Alright, let's check it out. That looks much better. In the last sample, we moved the mesh around to be able to see it. It would be a lot better to have a camera to actually move around. I've created a new mesh file, which is called yellowcube3, and it has a new vertex shader, but it's using the same fragment shader as last time. So let's copy the vertex shader and we'll save that as vscube3. And we're adding a new uniform, a new matrix that is the view matrix. So we'll call it UV matrix. And all we need to do is to multiply the position by that view matrix as well. And we can separate the camera from the rest. So we're getting the uniform location of that matrix. And we're setting it in our set matrix uniforms. So we're going to add another function to get the view matrix. We'll copy the previous sample and we'll save that as 11-camera HTML. And we'll use the right mesh file. We'll create a new matrix to hold the camera position and orientation, of course. And here we'll we'll just set the camera position at 3, and we'll add a bit of movement to it using our Z parameter. And we're going to set the view matrix, and we'll set that to the inverse of that camera matrix. So we're going to take some shortcuts because this is a rigid body transform. It's a lot easier to invert those. We'll look at that in a bit. First, we're going to add the function for the view matrix. And we'll add the matrix to the state as well. And this is just a regular 4x3 matrix. So we're going to go to the 4x3 and add a new function to create the inverse. So speeding this up, and this is using the fact that it is a rigid body transform. It just makes it a lot easier. You can transpose the rotation part and negate the translation part, and you're done. Alright, let's check it out. And there you go. You can see how the camera is moving in and out of the scene. We're going to improve on our global matrix state by adding a stack that will allow us to push and pop model matrices. So we'll make that an array, and we'll add in 2 pre-allocated elements, and then we'll add a count of how many we're currently using in that stack. We'll have to update our model matrix function to index into that array. And then we're going to add functions to push and pop matrices. So we'll just start by incrementing the count. And if that has hit the limit, we need to allocate more space. So that's using the state and the array length. Okay, so given that we have enough space, we want to copy the data over from the previously topmost matrix to the new topmost matrix. So we'll get a reference to the new top, and we'll get a reference to the one below that. And then we'll just copy the data over element by element. We could just copy the the 12 elements, but we'll copy the full 16 just to make it simple. Okay, and we need to return a reference to the new topmost, and popping will just decrement the count. We're not going to free any matrices because likely you're going to use them again. And for push, to add more space, we could double the amount of matrices, but we'll just add a new one when we hit the top. Okay. There. We'll save that. And let's copy the last sample and we'll save a new one. So we'll call this 12-scene graph, because that's what we're going to do in this sample. We're going to build a scene graph. And a scene graph is used to have some sort of hierarchical animations and using instancing, where you can have a single mesh and draw it several times at different locations and orientations. So we're going to add just a generic node for the scene graph. We'll call it DAG node, directed acyclic graph, and it's going to take a list of children, and it's going to have a local transform. So we'll just create an identity matrix in the constructor, and we'll copy the child list that we get passed in. And if we don't get anything passed in, we'll just assign an empty array. So let's create the prototype for the DAG node. We'll add the one function we're going to need for now, which is draw. Okay, and we're going to need another type of node as well. So we'll call that geometry. That's pretty generic as well. Create the prototype for geometry. Okay, we'll add the draw function. Alright, and we'll set the prototype of the geometry prototype to be the DAG node. It doesn't actually matter in this case, but in a real world sample you probably would have, more functions that you didn't override. Alright, so geometry, we'll have that take a mesh as a parameter, and we'll just save that a reference to that mesh in geometry, and in draw we'll just use that mesh and call its draw function. Okay, now in the DAG node, this is what it's going to make it hierarchical. So we'll push the model matrix and we'll apply the matrix in this DAG node, and then we'll loop over all the children and draw them. And this is going to mean that the transform in this DAG node is going to apply to all of its children and all of its children's children. So we'll draw all the children and then we'll pop the model matrix on our way out again. Model matrix. Okay. So we'll copy that and put it down here. And we'll create a new node, and we'll call it spin node. So we'll create a new DAG node. We'll pass it a list of children, and that list of children is just going to be a single geometry node containing our mesh, our cube. So this spin node will allow us to spin the mesh. So we'll build a list of children that we're going to add to a root node, and we'll iterate over x and y, making a 3x3 sort of plane, and we're going to allocate a node for each one of the positions in this plane. So we'll allocate a new node, make a DAG node, and we'll put a reference to the spin node in each one of these nodes. And we're just going to set the translation of the node. So we're offsetting it in the x-axis and offsetting it in the y-axis. So this is going to create a 3x3 grid of nodes that each one has the spin node as a child node. We shouldn't forget to add this new node to the list of children. Alright, and we'll create a scene node that is just a DAG node that holds all that list of children. So we'll copy the draw, and we'll put the draw down here. And instead of the model matrix, we're going to set this on the spin node. So it's going to rotate the spin node. It should rotate the local, the matrix in the spin node. So it'll apply that to the spin node. And we'll add some rotation to the entire scene as well. So we'll just make a rotation around the y-axis on the entire scene. So that's going to rotate the entire grid, and each item in the grid is going to rotate as well. And we'll pull the camera out a bit so we can see the whole thing. And then instead of calling mesh draw, we should call the scene draw. And that's going to iterate over all the children and draw them. So let's check it out. There you go. So you can see the entire scene is rotating around the y-axis, and each element in that grid is rotating as well. Let's do a textured mesh this time. I have this new mesh that I've added. It's called Mech Cube. You can see it has two new shaders, VSMech and FSMech, and it also has diffuse and emissive textures, as well as vertex texture coordinates. So let's start by writing that new vertex shader. We'll base it on the most recent one, VS Cube 3. So I'll copy that and paste that into a new file. And we're adding another attribute, which is the texture coordinates. Those are going to be two component. We'll call it a vertex texture coord. And that's going to be passed on to the fragment shader. It's going to use that to look up in the texture. So we're just adding a varying v-vertex texture coord, and we're going to pass that value straight through without doing anything to it. Okay, so let's save that, and we'll create our fragment shader. We'll base that on the latest one, FS Cube 2. Copy that, paste into a new file. We'll save that. Okay, so we have a new varying in, which is the texture coordinates. We're also going to do some texture lookup, so we're going to add new uniforms, sampler 2Ds. So we'll add one for diffuse and one for emissive. Okay, so let's do the color lookup. Create a new variable, and we use the texture2D function to look up a color in that texture. And we'll do the same for the emissive. And we'll combine those two colors and put that in the target color. So we'll use max of the color and the emissive. Alright, so we have a new attribute, so we need to get a new attribute location. So we'll call it vertex texture coord attribute. It's quite a mouthful. Alright, so we're going to need to do exactly what we've done with normals for texture coordinates, so we'll just copy that bit here, and We'll only do this if we actually get texture coordinates in the mesh file. We'll create a buffer for the texture coordinates, and we'll bind it and we'll fill it with data. Okay, so down in draw, we need to do the same thing for the texture coordinates as normals again. I'll copy that. Okay, so if we actually have that attribute, we need to enable it and then bind the buffer and specify the format of the data. And texture coordinates are actually 2-component floats, so we need to change that. Okay, so we also have some new uniforms we need to get locations for. It's the diffuse sampler and the emissive sampler. Okay, so if our material has a diffuse texture specified, we need to actually load that texture. So we're pretending that we have a function to load textures for us, and we'll write that later. So we'll just call load text and we'll pass it the file name of the image we want to load. So the same with the emissive texture. Okay. So let's add that load text function. Okay. Before I forget it, we need to modify the draw as well. So we'll set the active texture texture unit 0. And we need to bind the texture as a 2D texture. And we're setting the sampler saying that it should use texture unit 0. Okay, and the same for the emissive, but we're going to use a different texture unit, so change that, and we'll use texture unit 1. Oops. Okay, so we'll set the uniform to 1 instead. Alright, so let's go back to the load text function. So let's start by creating a texture object. And it's going to return that texture object and do something in between. So we're going to need an image to load the image data from the URL, and whenever it's loaded we want to actually create a texture out of it. And to kick off the loading we set the source to the file name, and that's going to asynchronously load it and let us know when it's done. So on load we want to bind the texture, and then we're gonna tell it to flip it along the y-axis, just to get it the way I'm used to. And then we're gonna upload the data from the image to that texture. So it's an RGBA image, and it's 32-bit, and that's the data to upload to the texture. And we're also going to set the some texture parameters for MIP mappings. So the min and mag filter, I'm going to set that to linear. Okay, copy that. Set the min filter, and also going to generate some MIP maps. Alright, so let's copy the scene graph sample. We'll change the mesh to the mech cube, and we'll save that as 13-textured mesh HTML. Right, let's give it a shot. That looks pretty unlit, so I must have made a mistake in the fragment shader. Max, oh yeah, I'm not using the diffuse, so we'll Modulate the color by diffuse. And there you go. We've only done boring primitives so far, so I wanted to show you that with the classes we've written, you can render some pretty cool stuff. I have this mesh called Marine. So let's save this new sample as 14-real mesh. So the mesh I have is a quite large mesh. It has normals and texture coordinates. It has diffuse and emissive texture. You can see the num indices. There's quite a number of indices in this mesh. So let's check it out. If you saw the intro of this movie, you probably recognize the guy from the Odin demo.